Okay, start it.
Hi, my name is Alan Jose Esquivel Jr., and today I will be presenting the drug analysis using thin layer chromatography, or TLC. Procedure summary. For a procedure summary, I will start off with sample preparation steps. Our first step will be labeling the culture test tubes in the following order. 1 is going to be our Tylenol, which are acetaminophen. 2 is going to be our aspirin, which is pure. 3 is going to be our Benadryl or diphenhydramine. 4 is going to be our ibuprofen. 5 is going to be our Excedrin. 6 is going to be caffeine. And then for our second step, we will be crushing all the drugs into the fine powder and place 1/4 of that powder into the culture tubes. Ensure that no solids are present inside the culture tube when adding the 2 mLs of methanol, which is going to be our solvent, and then screw the cap on. Our third step will be shake the culture tubes and allow for them to sit for 30 minutes to settle prior to placing it on the spot plate. Procedure summary. This is a continuation of our procedure summary, which is involved preparing the developing chamber and adding the sample to the spot plate. We started off by preparing the developing chamber by adding 5 mLs of methanol into a glass beaker and cover with a lid to allow for it to equilibrate for about 5 minutes. After those 5 minutes, we can start adding samples to the spot plates. Touching only the sides of the thin layer chromatography or TLC flat plate, we also draw a line about 1 centimeter away from the bottom of the TLC plate, which doesn't have a bottom. It's the same thing all around, just whatever you choose. But we want to make sure to have a line above the solvent in the beaker to avoid contamination amongst the samples. So just to make sure the solvent is not touching the samples itself, but touching the unmarked area of the TLC flat plate. Second, we place 3 drug samples in each of the TLC flat plate using a pipette to place a drop of the sample without squeezing to the TLC plate. So the way I did this is I got a pipette, dipped it, got a little bit of liquid, and just tapped it. Because if you do squeeze it, it is going to make a huge circle and it's going to pretty much overfill and everything and all that. So it's going to contaminate regardless if the solvent's touching the sample or not, because it's going to contaminate with the other samples. And then we allow for the spot, which is our sample, to dry and reapply the sample to the TLC plate for about a total of about 10 times. So I did it about 10 times. So I did it initially 1 time, which is the one we dropped, and let it dry, then we just continue adding. So it's a repeat process, but we have to be very patient in terms of like letting it dry and reapplying, and that should give us results at the end of the experiment. Procedure summary. This will be our last slide for our procedures. In this slide, we will be discussing developing the spot plate and determining the results. First, by placing the TLC flat plates in the separate developing chambers and covering with the lid. This will allow for the solvent to travel up the spot plate, and prior to reaching the top, we will be taking out the TLC plate and letting it air dry. When it air dries, you will be penciling in at least 1 centimeter from the top, which is also called our solvent front. Then for our recording and determining results, after giving the TLC plate time to dry, we measure the total distance traveled by our solvent, which is our methanol, from the initial penciled in centimeter. So we'll be measuring that space between the initial 1 centimeter penciled in and our solvent front, which is our 1 centimeter from the top. Secondly, we will then put on our orange goggles, and using the UV LED provided to us from our kit, we will view the drug spots on the TLC spot plate. By placing a dot in the center of each spot that we see on the TLC plate, which represents each drug, we would then measure the distance from the center of the spot to the initial 1 centimeter line. Third, We would then use the distances that we measured from each of our samples and divide them amongst the total distance traveled by our solvent, which will give us our RF values. Data summary. For our data summary, we'll be discussing the results we got of our distances and the total distance traveled by our solvent to calculate our RF values. Starting off with Benadryl, which is diphenylhydramine, it traveled a total distance of 4.9 centimeters, and the total distance of our solvent was 5.5 centimeters, which gives us an RF value of 0.89. For aspirin, it traveled a total of 5 centimeters, and our total distance traveled by solvent is 5.5 centimeters. Divide that and we get 0.90. For caffeine, it traveled a total distance of 4.3 centimeters. Divide that by the 5.5 centimeters, we get 0.78. For ibuprofen, it traveled 4 centimeters. Divide that by the total distance traveled by a solvent, which is 5.5 centimeters, we get a RF value of 0.72. For Tylenol or acetaminophen, traveled only 3.5 centimeters. Divide that by our 5.5 centimeters, we get 0.63. For Excedrin, it traveled a total of 5 centimeters, and divide that by our total distance traveled by our solvent, which is 5.5 centimeters. It'll give us an RF value of 0.90. Significance of the mobile phase and stationary phase. The main principle of the thin layer chromatography, or TLC, is the differential migration of a substance on an absorbent material such as the silica gel we used or alumina coated flat plates. The stationary phase would be the absorbent material, and what we used in this lab is the 2 silica gel flat plates. The significance of the stationary phase in this lab particularly is differing affinities of polar and non-polar molecules. Plus, the silica gel flat plate also allows forensic analysts to use black light or UV LED to identify spots after developing in the solvent, which gives us the RF value. For the mobile phase, is the solvent used for the separation based on the polarity of the substances. The importance of choosing the correct solvent can influence resolution, selectivity, and our RF values. In this lab, we use polar solvent methanol, which has a higher polarity towards amino acids and peptides, which should help us with the drugs that we are using. Different rates of movement across the stationary phase. Some factors on why some substances move at different rates across the stationary phase is because solvents such as methanol can have a strong polarity. This can dictate the rate of movement of each substance and compounds that are polar. Thus, we see some drugs have a stronger polarity, some drugs have less polarity. Polar compounds have a strong interaction with silica gel and may need more polar mobile phase to increase migration. As for non-polar solvents, they hardly interact with the silica gel flat plate, while polar compounds can be located not so far from the initial penciled in 1 centimeter baseline. So for non-polar, we would see more distance from the drug from the baseline compared to polar compounds or polar drugs being near the baseline, which is shorter distances. Calculating the RF value. To calculate our RF value, we'll be using the following equation. RF equals to the distance of the drug sample over the total distance traveled by our solvent. The retention factor of RF makes it possible to quantitate a substance movement by measuring the distance a substance traveled from the baseline of the 1 centimeter penciled in we made to then divide it to the total distance of our solvent, which is the solvent front that we penciled in the 1 centimeter on top on our silica gel flat plate. This will give us our RF value. The importance of the RF value is that it is a ratio that represents the relative distance the substance traveled when compared to the total distance traveled by the solvent. Thin layer chromatography. Thin layer chromatography has its limitations, thus it is why it is considered a presumptive test only instead of a confirmatory test. Reasons include is resolution, detection, quantification, size limitation, solvent dependence, sample processing and preparation, and lack of reproducibility. For resolution, it has difficulty in separating very closely related compounds. We could see this with our extradin, which has pretty much a majority of other drugs we're using, like acetaminophen and aspirin. So it's closely related to that. Thus, why it had a higher affinity to go higher compared to the other drugs. For detection, certain substances may not be visually detectable. For quantification, it lacks precision. For size limitation, the size of the plate to perform the test itself. We had to do 2 separate TOC plates due to only 3 of the samples fitting. For solvent dependence, the choice of the solvent can affect the separations of efficiency. Thus, we used a very highly polar solvent, which is methanol, because most of our drugs are very polar. Thus, we had to get pretty much a more mobile phase to be polar. For sample processing, poor separation and overlapping of spots can occur if overloaded with samples. How we said we can only fit 3. If we try to fit more, then we enter the state of contamination of other samples and affecting this test itself. And then the lack of reproducibility, which is pretty much inconsistent plate preparation and solvent can influence results. So even if you follow to the dot of how they did it, our results can vary and it could still not be the same. It'll still be present, it just wouldn't come out the same, maybe distance or anything like that. So that's why it lacks reproducibility. Thank you for your time, and these are my references. Have a great day.